Hi all. So in this video, we use one of the oldest, if not the oldest, methods to visualize transport barriers and invariant manifolds in 3 dimensions. So we will introduce the Poincare Map computation on the steady BC flow. The computation is actually very, very simple, and the idea is also very, very simple. There are 2 scripts. One script does the Poincare Map computation on the steady BC flow using the discrete, so using the gridded data, and the other one using the analytic data. We will take a look at both scripts. The Poincare Map ABC steady uses the gridded data. So what we do is we of course have the steady BC flow, and we import, so we do not use the analytic version of the steady BC flow, but in order to emulate and so actually in order to simulate the setting where you have experimental or numerical or data from numerical simulations, we use a gridded version of this velocity field. So it's basically a discrete gridded velocity data set. Of course, it will come with its own limitations because it won't be as accurate as the one as the analytic data set. So the structures that we will get here will not be as accurate. However, one can use the script also to compute or to run the Poincare map on your experimental data. We simply proceed then again by interpreting the velocity field, and the steps in order to compute the Poincare map for the steady BC flow are very simple. So in order to make use of this Poincare's idea, we require some kind of recurrence. So either some temporal recurrence, where we basically sample trajectories at regular time steps, which are periodic time steps, or we require some kind of spatial recurrence. So basically, you can define an intersection. So you can define a section, and you can launch trajectories from this section, and you can every time the trajectories re-intersect these initial cross section that you defined, you can plot the intersection point. In fact, that's eventually what we'll do. So we will seed very few trajectories. So keep in mind that here we will seed just 10 times 10 equally spaced initial positions on the grid defined by the z equals 0 plane. And we will use, however, very long integration times. So Poincare maps generally require very, very long integration times and few trajectories, however, to visualize invariant manifolds. Then we only retain the long-term behavior trajectories. So you compute the trajectories over a fairly long time interval, but you just keep track of the trajectories, let's say, for between the times 10 to the power 4 and 2 times 10 to the power 4. This is chosen to be arbitrary. However, it needs to be very long. And then you simply sample the trajectories at points which re-intersect the Poincare section defined by the z equals 0 plane. So every time the trajectory comes back and re-intersects this z equals 0 plane, basically touches the z equals 0 plane, you count it as an intersection and you plot the point. The idea is simple in the sense that you just need to integrate the trajectories. This is done here by simply using our integration function, which we have already covered in the introduction notebook on computing trajectories in 3D. And then, of course, this is all parallelized. So I take all these 10 times 10, which means 100 initial positions, and I just compute these trajectories. So fmaps is simply an array which stores all the trajectories, and then what you do is you compute the Poincare map. So you basically here you only extract. So you specify the time interval over which you want to extract the trajectories, which is not from the initial time, but you just want to extract, let's say, the last 10,000 time steps. You do a spline interpolation. So you basically, where you have basically one spline interpolation for each dimension. So of course, one for the x, one for the y, one for the z dimension of the trajectory. And then you iterate in time, and you check whether the trajectory reintersects the z equals 0 plane. You can do a similar reasoning by specifying the x equals 0 plane. You would simply need to change this argument here instead of choosing chord interp z interp, you would need to choose, for example, x interp. This would then compute the Poincare section for the x equals 0 plane, or this one would compute the Poincare section for the y equals 0 plane. However, let's remain for the z equals 0 plane. You compute the intersection points, which will of course be some substantial amount of intersection points. And then you simply plot all these intersection points. And what you see, you get these beautiful tori here, which are very precisely highlighted. Again, take a look here. So beautiful tori here, very precisely highlighted, which are related to the elliptic LCS. Now, this is assuming that the data that you have is on a gridded domain. Now, if we use analytic data and do the same reasoning, then you can see that the structures I get are even more precise. You see all these beautiful, nice little tori here surrounding the major tori, which are only scarcely visible here. This mismatch is just attributed to the interpolation. So just because so here, of course, you're using analytic data. So you're using an analytic velocity field, which makes everything much more precise than using an interpolated version of the velocity field. However, you can see that the structures agree to a very good extent. With that, I would like to conclude this video on the Poincare map applied to the steady BC flow. Again, I'm happy to answer any questions that you might have. If not, see you in the next video.